Okay, so I'm going to be recording. Okay, so we were talking about electric fields, and we're going to be working on this topic today, this week. So we were talking about electric fields, and remembering that an electric field is going to be this invisible, invisible thing that's going to surround any sort of charged object. Okay. And remembering that a charged object can have different types of geometries. I'm sorry, the first analysis or the first situation we're going to be talking about is a charged particle that's a point. It doesn't have a geometry, a figure, or a mass, or anything like that. It's just a point. But we can have other situations where we're going to have objects that have dimensions. And we already talked about a cylinder, and a cylinder is important because it kind of models what a cable is going to be, or a sphere, or parallel plates. And also, if we have many things that have an electrical charge in the same space, each of them is going to generate an electrical field, and these electrical fields are going to interact. And depending on where I put another charge, these electrical fields are going to affect that, Always try to remember, because we're working with things that are abstract.
Professor, we can't hear you.
Am I muted? No, or is it? It's a connection. Let me change microphones. The connection is unstable. Yes, go ahead.
Can we turn off the lights in the front, or?
Yes, we can do that. I changed microphones. I changed microphones. Can you hear me the same? Or
yes, but
yeah.
I think it was more of a connection issue, not the microphone.
Because there's two microphones, and I forget which one works better. I'm going to change to the other one. So is it okay now?
Yes.
Okay.
Yes.
Remember a couple of things. Well, three things. If there's anything you guys need, so like Lisa mentioned about the lights and all, I just mentioned, and we can do that. It's not a problem. Secondly, if there's any sort of audio, video, or whatever issue at home, let me know in the moment. So interrupt me, okay? Because like my wife says and knows, I can keep talking for 45 minutes and not shut up. So interrupt me. And the other thing is that remember that all the sessions are being recorded. Okay, and the purpose of the recordings are uploaded the same day to the playlist. So if for whatever reason at home you guys didn't catch something, it's being recorded. Okay, so just remember about the recordings. Okay, so as I was mentioning, since we're going to be working with things that are abstract, try to think about electrical charges and current. Try to think about fluids or liquids. So imagine that we have a river or something where water is flowing, okay? And we put a rock into that river. If the river is going that way, imagine that the river is the electrical field. And I put a rock there, the river, or the movement of the river or the electrical field is going to make the rock move that way. It's the same thing here. If I have an electrical field, the electrical field is this, it's like the water, is this thing that's pushing. If I put something there, and the something, for the river, it was the rock, but for these situations, it's going to be a charged particle, it's going to want to move it. Now imagine that instead of just having one flow of the river, I've got intersecting flows of water that are coming from different places and have different pressure. If I put a rock there, the rock is going to move to wherever the pressure is most, okay? Same thing is going to happen here. If I have many things in space that have an electrical field, the electrical fields are going to interact. So depending on where I put something, that something is going to want to move depending on the whole effect of the electrical fields. And we're going to be talking a little bit about that. And the bonus that has to do with electrical field hockey shows that. Depending on where, and I'm very curious because like you mentioned that you got into a fight in the previous class. I mentioned about the electrical field hockey, and I started getting a lot of WhatsApp messages. Where do we upload it? Can I consider this? So some of you were already trying to do the exercise. That's probably the motivation for the bonuses. So that's good.
With 7 charges.
You did with 7? That seems about right. It's a bit, the trajectory is a bit complicated, so you need a few charges to be able to do that. So 7, well, so Diego already gave us like the baseline, so that you guys did 7. So if nobody does less than 7, then you probably have got the baseline to do to have the highest bonus point. Everybody's gonna have a bonus point, bonus points. It's mandatory. You need to turn it in, but I'm going to give points to the first 3 spaces, depending on the position. And so, if we have an electrical field, the electrical field can be represented a few ways. One way is that the electrical field is going to be the force exerted on a charged particle by unit charge. Okay. So I thought I had arrived in a magical place. There was this sort of like twinkling thing. So it's going to be the force, the electrical force by electrical charge. So that's one way we can represent. That's a general way in which we can represent an electrical field. Now, we're going to be we're going to be going in steps. So the first situation that we're going to analyze is the electrical field of a point charge. Just remembering that a point charge is something that has no geometry. It's something that's just located in space and has an electrical charge. We don't care about its dimension, and that electrical charge generates an electrical field that radiates outside. So if the electrical field is given by F
Professor,
yes.
what did you say? What was the definition of point charge?
Okay, a point charge is going to be, or the way we're going to represent it, a point charge is going to be an electrical charge that exists in space, but it has no dimensions. So it's just going to be, it's literally going to be a point in space that has an electrical charge. But since it's a point in space, we don't care about its dimensions. So it doesn't, it isn't long, it isn't wide, it's just a point in space. It's a very ideal representation. So it's just going to be a point in space that has an electrical charge. And that electrical charge is going to generate an electrical field that's going to radiate out of it. And so if the electrical field is the force by unit charge, we know by Coulomb's law that the force is K divided by the charge, or multiplied by the charges divided by the distance squared. So this here is the force according to Coulomb's law divided by the unit charge. That gives us that the electrical field for a point charge is going to be directly proportional to the charge itself, and obviously inversely proportional to the square of the radius. So if I put a charge in space, a point charge in space, that's going to radiate an electrical field. That electrical field is going to be directly proportional to the charge, and we're calling that Q source, divided by the square of the distance. It's going to radiate by the square of the distance. Okay. Oh, by the way, we're going to go. No, we're going to do the Valentine's bonus in a bit. I remember because I read the poems, and some people referenced Coulomb's law and all that, which is interesting. So yeah. It's actually, it's interesting because in an electricity and magnetism course, because of the sequence, we first talk about electrical charges and we talk about magnetism towards the end of the course. But you guys are much more familiar with magnetism. So if there is something that has a magnetic field, you can't see the magnetic field. But if you grab something metal, you're going to feel the force. So you're more used to magnetic fields. You're not that used to electrical fields. I think that the most common thing that happens with electrical fields is when you give a shock to somebody. When you give a shock to somebody, that means that you guys are getting charged electrically because of friction, because of whatever. And basically, you're like that point charge there. You're emanating an electrical field. When somebody touches you, that generates an electrical force that transmits charge to the other thing. But you don't know that you're radiating that electrical field, right? But if we were to look at you as a charged, I'm sorry, as a charged object, depending on if electrons were removed or added to you, you would have that field going outwards. And that's what we're talking about here. Okay. So again, if you guys want to have your water bottles or whatever here, you may, as long as you're closed. I don't have a problem with it. Now, if I have many things or many objects in space, each of them with their electrical fields, these electrical fields are going to interact. And there's going to be a resultant or an equivalent electrical field that's product of all these interactions. And you guys are used to this because you do the free body diagrams of forces. And so if there's many forces interacting, there's going to be a resultant force of all of these. The electrical field is exactly the same way. Now, this is important because we're going to be seeing two types of situations here in at least this unit. There are going to be some things that are vectorial and some things that are scalar. Do you guys remember the difference between one and the other?
One has direction.
Exactly. The vectorial are things that have magnitude and direction. So that means that if I have an electrical field, the electrical field has a value, a magnitude, but it also has a direction. It's pointing somewhere. Okay. So electrical fields, like forces, they're vectorial. They have magnitude and they have direction. And that's very easy to remember because the positive charges, the electrical field is going outwards, remember? And the negative charges, the electrical field is going inwards. There's going to be some other concepts that are going to be scalar. A scalar is something that has a value but doesn't have a direction. Okay? So energy is scalar. Energy is scalar. There's a certain amount of energy in joules. That's an amount, but it doesn't have a direction. Okay, it's an amount of energy. Power is not vectorial. So have you heard somebody say, well, this device can consume or generate electricity at 100 kilowatts. You've heard the term kilowatts or watts, right? That's power. That means it's the amount of energy that can be transmitted, but it doesn't necessarily have a direction. It doesn't say that the kilowatts are pointing that way. Okay, so that's the difference between a vector and a scalar. Okay, and the electrical field is a vector. So in this example here, we've got two positive charges. Notice that one is smaller than the other. These two charges are generating an electrical field each. And because both electrical fields are interacting, there's going to be a resultant electrical field. And we apply the same rules we apply with forces and free body diagrams for electrical fields. Okay. This example or this problem, I had asked House Turndown for Watts. I asked Juan Ignacio actually to work on this problem. And let's talk a little bit about this one. So the Earth has an electrical field. Okay. By the way, certain objects in space, remember, everything can have a gravitational field. We have gravitational fields because we have mass, but the gravitational fields that we have are really unimportant. The Earth is huge. So the Earth's gravitational field with regards to us, that's what makes us stay here on Earth. The Earth's gravitational field with regard to the moon's gravitational field, those interact, and that's what makes the moon have an orbit. Okay. So everything has a gravitational field as long as it has mass. But if we're small enough, it doesn't matter. Everything can have an electrical field. Okay. And everything can have a magnetic field as well. The Earth has an electrical field going outwards. Okay. It has an electrical field surrounding it. It's an electrical field that's similar to a positively charged object. So this drawing over here, this was my attempt to do drawing of the Earth. This is the seas and this is Earth. And this is the Earth, and there's an electrical field going outwards. Okay. It's debatable if this image is from last year. It's really debatable if my writing has gotten better or worse. Last year, I didn't have the pen and the tablet. I did all of my drawings with the mouse, and they came out like that. I don't know if the drawings are going to be better with this. What I do know is that with the pen, it's quicker. I used to take about half an hour to do a drawing like this, like the one you see here. But with this, it's as ugly, but it's quicker, at least. So imagine that we have the Earth and there's an electrical field going outwards. Okay. At the surface of the Earth, around here, because remember that the electrical field is going to depend on where we're located. The closer we are to the object, the stronger it's going to be. The farther we are to the object, the weaker it's going to be. So somebody took a measurement, and at the close to the surface, the electrical field is 100 newtons divided by Coulomb. Now, let's assume that we have a drop of oil. This drop of oil is very, very small. Since it's so small with regards to the Earth, we don't really care about its mass. It's just a drop of oil. And if this drop of oil is this little black spot here, if that drop of oil has a charge in it, and I put it close to something that's charged like the Earth, then there's going to be an electrical field, and there's going to be a force. Always where there's an electrical field and a charge, there's going to be a force. So there's going to be a force going up, but let's assume that this very small oil drop has a mass. Okay, so if it has a mass, it has a weight. So the mass is going to make the oil drop, but the electrical field is pushing it upwards. So the question is, what would the charge have to be on that drop so the drop is floating, it's suspended? So the weight is compensated by the electrical force. So we know that if we do a free body diagram here, which is what we're seeing here, this is the drop of oil. There is going to be a force going downwards, which is the force that has to do with the mass, which is also equivalent to the weight. And then there's going to be an electrical force going upwards. This is actually a Q that has to do with the electrical field. If I want the oil drop to float, those two forces have to cancel each other out. Okay. So the force of the mass, which is equal to the mass times gravity, has to be equal to the force of the electrical charge. Now, what's written here that's kind of small, and I'm just going to write it down here again, a bit larger, is that the mass times the gravity, which is the force, is equal to the force on the charge. The force on the charge is going to be equal to, we know that the electrical field is the force divided by electrical charge. This means that the force on the charge is going to be equal to the electrical field multiplied by the charge. So this is going to be equal to the electrical field multiplied by the charge. From here, we can find that the charge is going to be equal to mass times gravity divided by the electrical field. And over here down are the substitutions that we do for that. This is a G, by the way, it's not to confuse with the Q. And that's going to give us that the charge should be 1.96 times 10 to the minus 16 coulombs. That would need to be the charge of the oil drop, so it's suspended because of the electrical field. Okay. Something that I think you guys have noticed, you should have noticed up to this point, when we're working with electrical values, we're going to be working with very small values. So the charge, it's times 10 to the minus 16, times 10 to the minus 19, times 10 to the minus 10. The values are going to be very, very small. A 1 coulomb electrical charge is a huge electrical charge with regards to any. Charges are going to be very small, the values that we're working. Okay. Okay. Questions up to this point? We're going to be doing some more exercises, and you guys are actually going to be doing some exercises by the end of this week for next week. Questions up to this point before we go to do some more exercises. Examples, I'm sorry. Over at home, are we okay at home?
Yes.
Okay, good. Okay. So right now that was a point charge, but we're also going to be talking about the different geometries. But before that, we need to address another topic, which is Gauss's law. And I want to prepare you psychologically because we're going to be using some integrals. So I need you guys to dust off your integrals. Yeah, you already saw integral calculus, right? That was last semester. Yeah, right. Yeah, last semester. Yeah. So we're going to be using some integrals there. So I need you guys to prepare yourself psychologically for that. So, but we'll get there. Because I know you guys love integrals. And let's look at these situations. And we're going to be doing it with the interactive electrical field simulation, which is this one that we've got here. Let's just try to understand how these electrical fields interact, okay? And so we're going to be seeing these five. We're going to be seeing these five situations. And what we want to see here is we just want to try to understand how the electrical fields are interacting. This is actually going to be a question in the first exam. I'm going to give you any of these situations, and I'm going to ask you to draw the electrical fields, just so we understand how they interact. And well, we're going to see it here, but you guys probably did this experiment. You may have done this experiment in high school or maybe in secondary school. You guys can click on the simulation. Okay, you can click on the simulation. You can also do it at the same time as I. And I'm going to be switching screens. By the way, just question over at home. Right now you're seeing the simulation, right? Black screen.
Yes.
Okay, if I do this, do you now see the PowerPoint?
Yes.
Yes.
Okay, because Zoom has different sharing options, so. Okay, so the first situation is sketch the electrical field around the following arrangements of small charge object. These are point charges, okay? First, an isolated positive charge. We already did this, by the way. So how would the electrical field look for a small isolated positive charge? We already did this, remember? What happens? For a small isolated positive charge, what we need to remember is that the electrical field is going outwards. That's the way it's interpreted and represented. By the way, somebody might ask, wait a minute, but why? Why is it defined that a positive charge is going outwards? Somebody said that that's the way it was gonna be. Don't ask me, okay? I mean, something in an electrical and electronics things that might be stressful for some people, but that's the way it is. We have to take certain conventions. So from now on, a positive charge, the electrical field is going outwards. If somebody has a controversy with that, I'm sorry, but don't have a controversy with that. It's going outward because somebody decided that it was gonna be going outwards. There are certain things that they're gonna be that way because if we do it differently, so let's say that for me, the positive is gonna be going outwards. And then Estrella says, no, for me, it's gonna be going inwards. It's gonna be chaos. We need to have a baseline, okay? So that's this one. So again, this is gonna be a question in the exam. You guys need to remember this. Positive charges, electrical field is going outwards. And what we already saw, the further away we are, the weaker it is, the closer we are, the stronger. That's the basic rule. Okay. Is it okay if we go long? Over at home, you may stand up, do whatever you want. I can't see you anyways. Over here, if you guys need to stand up and walk around a little bit, do it. If you guys need to go to the bathroom, go ahead. If you're gonna be doing either of those things, just let me know, okay? Just don't stand up and walk away because I'm gonna think that this was too stressful and you're gonna jump out the window. And I'm gonna get in trouble if you do that because they're gonna say that my class generates stuff. So just make it
How did you describe the charges going?
Oh.
around?
for a positive charged object, the electrical field is always gonna be pointing outwards. So the arrows are always gonna be going to the outside for a positive charged object. They're always going to be going to the outside. But by the way, you guys, I really commend you guys because I saw it in this class and I also saw it in the previous class. Remember Dr. Dan Shunk?
Yes.
Okay. One of his pet peeves, besides the fact that he thought that you guys hated him because you didn't interact, he was so stressed when he gave the talk to you guys. What did I do wrong? They didn't interact. I'm like, that's the way they are. Don't worry about that. But one of his pet peeves is that students don't take notes. And even he teaches classes in the graduate program for masters, and he's really stressed that students don't take notes. And so I'm noticing that you guys are taking notes, and that's great, by the way. I commend you because it's not that common for students to take notes. So it's good for you guys to take notes. Just remember one thing. If I'm going too fast, let me know if you're taking note of something, but also remember that everything is in the PowerPoints and in the videos, okay? But if you need to take note of something, stop me. But it's good that you guys are taking notes. He gets really stressed when we're in a meeting and he's talking, doing stuff, and everybody's like this. It's like nobody's taking notes. So it's good that you guys do that in the previous class as well. So that's the positive charge. That's the first situation. I'm gonna clear this. The second situation says an isolated negative charge. And we had already seen that situation as well. An isolated negative charge. What's the difference? The opposite. The electrical field for a negative charge, the convention that we're taking is that the lines are going inwards. A negative charge, the lines are going inwards. But the same principle applies as the other one. The closer we are, the stronger it is, the farther we are, the weaker it is, okay? But the lines are going inwards, that's the important. Now, the lines are important because what's going to generate force is the interaction of those lines. The interaction of those lines are what generates, or what's going to generate forces. Okay, so that's the second situation. The third situation is two positive. Okay. Everybody shout, está ocupado, está en clase. Thank you. These are people from the banks. And it's really annoying. And if you get calls from these people, I know that it's a job and people have to do that, but I do not like getting called by the banks. So I do that. I'm going to be doing that in every class. If the bank calls or it's a number I don't recognize, I'm going to ask the students to yell at them. I give the telephone to Sarah. I've been doing that as well. I just give the telephone to Sarah and Sarah's like, hi, my guy's busy. I'm Sarah. Do you want to talk to me? And that's fun for us, but I know it's not fun for the people we're calling. What really annoys me is when they call, when we get calls. Have you ever gotten calls from the funerary at lunch?
From Galloso.
At lunch, yeah, at lunch. I mean, I'm trying to eat my lunch. My birthday's coming up and I'm getting older and I get a call from Galloso to see if I want to plan ahead when I'm going to die. And we do have to plan ahead. We do have, I mean, I'm not saying that's not important, but not when I'm sitting down for lunch. Okay, going back to happier things. Situation 3, 2 positive charges that have the same magnitude. So I'm going to go back over here. Now we're going to put 2 charges that are positive. I'm going to put 1 charge here, and I'm going to put 1 other charge here. How are the electrical, what's happening with the electrical fields with these? What do you guys see?
They like have a line that separates them
Yes, and why is that imaginary line happening?
because equal signs they repel.
They repel. So basically, we're talking about the arrows. So remember that for a positive charge, the arrows are going outwards. And so if I put 2 positive charges, the arrows are going to be going outwards. So what's going to be happening with the arrows? They're going to crash into each other, right? So there's an arrow going this way. There's an arrow going this way for this charge, and then there's another arrow going this way, and they're going to crash into each other. That crashing into each other, that kind of generates that sort of imaginary line or barrier that Andrea was talking about. That's represents the repulsion force that's happening between 2 positive charges. Actually, this representation isn't, it's very square, the way this drawing is done. But if we wanted to do this a bit more elegantly, the way the lines interact in real life, we would actually be looking at this.
Professor, I have a question because
Yes,
you
go
said
ahead.
something, but it's not about this topic.
Okay, go ahead.
Oh, it's because you said a word and I remember about my poem and I wanted to ask you if we were gonna read the poems.
No, yes, we are. Yes, no, I've got that completely in mind. I want to be, I already read them and I believe I want to be entertained. So yes, we are going to read them. Yes, and we are going to read them. I'm going to give it a few minutes before we leave to read them. Yes.
Okay, thank you.
Yeah, it's not, the bonuses are not just for you guys, they're for me as well. So if we were to draw this a little bit more, I'm not gonna say elegantly, but a little bit more curved or continuously rather, we would see that the charges, the electrical fields are going straight. But the moment I put another charge there, the electrical fields interact. And so they generate this sort of bouncing effect that's curving the electrical field. You see that? We don't see that with the original arrows because they're very straight. Did you guys ever do this experiment? And I think we're going to do it in one of the lab practices. But did you ever do this experiment in wherever? I think they even do it in kindergarten. Well, I'm not sure they do it in kindergarten because of the electricity, but this experiment where you grab, you put a plate with oil in it, any sort of oil, even motor oil or cooking oil. It has to be oil. And then you sprinkle metal things on top, like metal. They're called shavings. Little like you sprinkle metal on it. But even you don't need to sprinkle metal. I remember that if I'm not mistaken, the experiment I think can also be done with pepper or some sort of thing that you can put on the oil that you can see. And you just sprinkle it there, and then you grab a battery, any sort of battery that has a positive and a negative, and you just put 2 cables into the oil. You're going to see that the shavings or the pepper is going to start doing that pattern. You can actually visually see that pattern in the oil. And that pattern is because the moment we put the electrodes, which is basically the positive and the negative. In this case, it's positive and positive, but we're going to see the positive and the negative in the next slide. We're generating an electrical field around that, and we're going to see that they generate this this sort of pattern. Yes, yes, go ahead. We can see this pattern forming, and that's a very simple experiment. You guys can do it. You guys can do it at home, and you can do it with any sort of. So you've done that one, Diego? You've done that
Yeah.
previously? Was it in high school or in secondary
Use it
school?
as a final project.
Oh, really? In a physics class, I imagine, or something like that.
Yeah, we're shooting at a tree.
Did you do it with the shavings, or did you do it with
That shaving.
metal shavings?
Yeah.
And so it's actually going to represent, depending on what you use, it can either represent the electrical field or the magnetic fields, because magnetic fields interact in a very similar way. Okay. Here it is. Here it is. Okay. The next situation is two negative charges of equal magnitude. And so what's going to be happening with the negative charges is that if I grab a negative charge here and a negative charge here, what's happening there? What do we see there? I'm going to try to visualize it the way Andrea visualizes it, because I thought it was a very interesting way of seeing it. What's happening with the interactions of the electrical fields there?
But the same, but now we're going,
Correct. For the negative charges, the electrical fields are going inwards, but since both charges are the same, there's again this sort of imaginary barrier where the two electrical fields are crashing into each other. And so we're going to see the same, a very similar effect here. So we're going to see a kind of bending, but now it's going inwards. And also here as well. So we're going to see these electrical fields interacting, but again, they're going to be crashing into each other. And that crashing into each other is kind of defined by this here in the middle. Like Andrea said, it's the same situation as the positive ones, but the only difference is where the electrical field is heading. This interaction generates the repulsion force that's going to happen for the two negative ones that are of the same sign. So the repulsion rule for charges that are the same are actually because the fields are interacting with each other. Okay. Remember, if anybody has any questions.
So that would be attraction.
No, it's the repulsion as well. He said because
Yes. Okay, yes.
they're crashing into each other. So in the other one, the arrows were going like this. That means that they're opposing. In this one, the arrows are going this way, but they're pulling.
That means because I thought it was one positive and one negative.
No, it's both negatives. And so it's going to be a repulsion force as well. Remember that the repulsion can be interpreted as somebody either pushing or pulling, but in a way that the charges are trying to be, they're trying to get separated. And the last situation is what's called and we're going to be referencing this concept, or you're going to be hearing this concept, an electric dipole. By the way, it's dipole or bipole. And as the name, no, it can be either one. It could be either one. So we could see it as electric dipole or bipole. It could be either one. But basically what it means is that actually they can be interchangeable, but I believe the more correct term is dipole because they're different. And it's basically, we have two charged objects or two things that have an electrical charge that are different. And of the same, assuming that they're of the same magnitude. And curiously enough, that difference is going to generate an interesting interaction. That's going to be really useful for electrical things and magnetic things moving forward. So now I'm going to grab a positive charge and I'm going to grab a negative charge. Both of them are of the same magnitude. So what's happening there with the electrical fields? In the case of the positive charge, the electrical field is still going outwards. In the case of the negative charge, the electrical field is going inwards. But what's happening with with both electrical fields? How are the electrical fields interacting
Yeah,
there?
try.
They attract because one arrow is going into the other one. So instead of the arrows crashing or being separated, they're kind of feeding into each other. So this is actually what you would see in the oil experiment. Or most likely this is what it would represent. The fields are interacting. So what's happening is kind of like something like this. And this is basically the representation of an attraction force. And this interaction with the electrical fields, where one arrow, which is going outwards, interacts with the other arrow that's going inwards to the other charge, is what basically represents an attraction force. Now, one curious thing about electricity and about magnetism is that with electrical charges, there can be the possibility of a positive, positive, negative, negative. Those are going to be repulsion. And then there's a dipole with positive, negative, where one feeds into the other. With magnetism, we're always going to have two poles. We have a negative, it's not called negative and positive, it's called north and south, where one feeds into the other and generates this magnetic field of either attraction or repulsion, depending on the pole you're closest to, and if it's north and north or south or any combination. But in magnetism, north and north is not going to generate a magnet. Go ahead.
One question, so what, is the north of the earth is a negative? Because the compass points to.
Oh, no, in the case of magnetism,
Oh,
when we're talking about magnetism, the terminology we use is north and south rather than negative and positive. Okay, so we don't necessarily say that the north is positive or negative. It's just a reference with regards to one pole and the other one. Okay, so in the case of the magnetic fields, when you have a compass, the metal part is going to be pointing to the north. Okay, and that's a reference we have here on Earth because of the magnetic field of the Earth. Okay, but we don't necessarily call it positive or negative. Okay, it's going to be a different concept. But what is important is that it's a dipole. Okay, yes, go ahead. Okay, and so that's going to be the positive and negative interactions. Okay. Okay, so questions with these concepts of how the electrical fields interact. Okay. And if we have, right now we're just talking about two of them, but if we put more here, if we put more charges, then the electrical fields, all of them are going to interact. And there's going to be in the end, there's going to be a total electrical field having to do with all of the interactions. Okay. And that's the next thing that we're going to be talking about. Okay. And these are just the representations of what we just talked about. And these are in the PowerPoint as well, but you can do them in the interactions. Okay. Now we're going to be working on this. We're going to be working on this problem. Let's assume that we have two charges in space. two charges in space. Both charges have the same value. They're 1 microcoulomb, but one is positive and one is negative. Now, we're representing a two-dimensional space. Fortunately enough for you guys, we're just going to be working in 2 dimensions. We're not going to be, I think we're not going to be working in 3. Well, no, in magnetism, the magnetism unit, we are going to be working in 3 dimensions for some stuff. But right now for this, we're going to be working in 2 dimensions. So we have a 2-dimensional plane. We've got 2 charges that are actually both of the same value. They're both positive. We've got one charge here and another charge here. What's the separation of those 2 charges? What's the distance that separates them? Assuming that the axis are in meters.
2, 4 meters.
It's actually, it's from here to here. It's 1, 2, 3, 4 meters. That's the separation. They're separated by 4 meters. And there's 5 situations here that we want to analyze. There's 5 situations. 1, there's one situation, which is this one here. There's another one here. There is another one here. There's another one here. And there's another one here. There's 2 charges in space. I want to know, and does everybody agree that these 2 charges, each of them is going to generate an electrical field, and the electrical fields are going to interact? Okay. I want to know if I place myself in point number 1, what is the total electrical field or effect if I'm located there? What is the total electrical field effect if I'm located in spot number 2? Or spot number 3, or spot number, I wrote 5 twice. This one is 4. In spot 4 or in spot 5. Depending on where I'm located is going to be the different the effect of the total electrical field. And why do I keep mentioning where I'm located? So imagine that I'm a charge and I place myself in any of those spots. I'm going to be feeling a different effect of the electrical fields depending on where I'm at. And we want to know what that is. And we're going to do those 5 situations. Yes.
The spheres are not moving, right?
Yes, it's very important. It's very important. Estrella's question is important. So right now we're in the electrostatics unit. So it means that the charges are fixed somehow, but they're fixed. They're not moving. Your question is important because right now we're talking about electrostatic charges. Charges aren't moving. The whole situation of electrical fields, etc., it changes if the charges are moving. Any sort of charge, moving or not, generates an electrical field. Moving electrical charges generate magnetic fields as well. So for example, the charges, if they're static, they're not generating a magnetic field. But if the charges were moving, the movement of a charge automatically generates a magnetic field. So that's a different situation. So right now, the charges are not going to be moving unless specifically stated for the problem for a particular situation. Okay. So in this case, they're not going to be moved. Okay. This is a weird question. It's a weird question for me because I like to play with words and all that. Okay. You guys took a statics course, right? And that was physics of things that weren't moving. And you understand the word statics. Static means not moving, right? What was the next course called?
Dynamic.
And dynamic means movement. Is that clear to everybody?
Yes.
Okay. Have you heard the word thermodynamics?
Yes.
What do you think thermodynamics is? You don't have to be experts on that. Either here or at home. What is thermodynamics? It's heat, right? It's heat. It's things that have to do with heat. We're not mechanical engineers here. None of us are mechanical engineers. We can just say that thermodynamics are things that have to do with heat. We okay up to this point?
Yes.
And right now in this course, we're talking about electrostatics. And these 3 weeks, I think I can ask you, Giselle, are you there, Giselle? Going once? Yes, Giselle. Right now, we just said that thermodynamics is things that have to do with heat. And if I were to ask you, Giselle, what does electrostatics have to do with? What would you answer? If you're there, Giselle. What is that's actually going to be a question in the exam. What is electrostatics? Are you there, Giselle?
Yes.
Oh.
I'm just thinking.
Oh, you're thinking, okay, let's put, you could please turn on your, you guys, when you're at home, if you could please turn on your cameras when I call you. So what would electrostatics be, Giselle?
That is it like electricity that is not moving?
Yes, perfect. And remember to turn on your cameras, you guys, and if you can't turn on your cameras, let me know. You don't need to let me know why, just let me know, okay? Yes, it's electricity that's not moving, like the charges, right? Are we okay up to this point? You took a statics course, you took a dynamics course. You know thermodynamics is things that have to do with heat. And you already know that electrostatics are electricity that's not moving. Have you ever heard the term thermostatics? No, right? Doesn't even make sense. Have you ever heard the term electrodynamics? Really? Why then? Think about that a little bit. I'm not going to answer right now. Remind me next class. Think about that. Electrodynamics has to do with heat. We all know what heat is, even if we're not mechanical engineers and we're experts on that. But then why isn't there something called thermostatics? And if electricity has to do, electrostatics has to do with electricity that's not moving, then why isn't there something called electrodynamics? Let's leave it there. Think about it from today and Tuesday. Do not sleep. Have nightmares about that. And I'm going to touch upon that on Wednesday again. Okay? Because everything has to do with movement. Okay? Everything has to do with movement. Think about that. Okay. Now, before we do the examples, I just want to formally set up the bonus, because I mentioned it last class, but I just want to formally set it up. So it's the electrical field hockey. First off, this is a house activity. Okay, it's a house activity. So you have to turn it in houses. The link to the simulator is here in the PowerPoint. You can see it there. And so basically what you guys have to do is that in this simulator, we have a puck that's a positively charged point, and we can put electrical charges around this point, and the point is going to move depending on the interactions of these electrical charges. And there's some notes here, one that says trace, another one that says field. I can see the electrical fields there if I want. And when I click start, imagine that the black point isn't there, but the rest of the charges are, and they're not moving, they're fixed. Let's say that I drop a charge there. The moment I drop the charge, the electrical fields are going to interact. So the blue and the red aren't moving, but the black is going to move because there's something pushing it, which is the resultant electrical field. So depending on how all of these interact, the puck is going to move somewhere. Okay? Yes.
Does the puck need to be positive, or can I do it in negative?
Oh, that's what I'm going to be setting up right now, because I didn't give kind of like the parameters for you guys. So first off, let's assume that the puck is positive. Okay? We're going to assume that the puck is positive. I'm just going to say this, Diego, without going into detail, but if you put the positive and you do a very similar array with opposing charges, like the one you did, you should get a very similar result. Okay, assuming the same values. Okay. So first, let's assume that we have a positive charge. And there's 3 levels of difficulty. The first one, oh, The first one is actually practice, which is really because we just have to put something positive here and it's going to go there. Then there's level 1, level 2, and level 3. Okay. So for level 3, you have to make the puck go into the goal. The puck is positive. Somebody else asked me a question in the WhatsApp. We are not going, there's a value of the mass here on the bottom. Leave it as it is. Don't modify the mass. Don't modify that value. Leave the default. Okay. Leave the default. You can use as many charges as you want. Everybody's going to get points. But there's 3 houses. The house that uses the least amount of charges, I'm going to give additional points, and so on going down. Okay, so everybody's going to get extra points. But the house that has the least amount of charges, doesn't matter if they're positive or negative, they can be combined as you wish, is going to get additional extra points. Okay. You're going to turn it in via the corresponding Blackboard forum by Friday before class. And the way you're going to upload it is you're going to do a video. Okay. Yes. Yeah.
Does it count as cheating if I go above the obstacles and just, because you can go above?
No. Oh, I understand. You mean?
Like you can go, the charge can go outside the page.
You mean like the puck doing this?
Yeah.
No, it's not cheating. I'm not going to consider it as cheating. Technically, this is like the field, right? So let's assume that the ball can go out and come into play again. Okay. Let's assume that. Okay. So yeah, they wouldn't be considered cheating if it goes around. Okay. Ask these questions. And yeah, go ahead, please.
Professor, I think that it should be interesting that we all pass the obstacles instead of like going around them.
Okay, let's do this. No, it's fine. It's fine. I like the competitiveness. Let's do this. The baseline, I'm not going to consider it cheating if you go over, but if you don't go over, that's going to be considered a tiebreaker, a point for the first place.
I did it 2 ways.
Okay, so that could be valid as well. So I noticed that then the motivation for this group is competition, because for the rest of it, does anybody have a question with electrical fields? And some people are snoring. But with this, it's like if it's a 1.5 mass, it's gonna work. If I bring over Wayne Gretzky to help me out with the hockey, does that? So everybody's very engaged. So I like that. That's fine. So that's going to give you extra points. Okay. Now so you're going to upload a video to the Blackboard forum. I suggest please upload the link, the YouTube link to the video, so you don't have a problem uploading a video file. Okay. Because it's going to be a short video, you shouldn't have a problem uploading it to YouTube. Now I'm going to give additional extra points just because I like to, and if you're doing this, hopefully you're understanding what's happening. There's another 2 difficulty settings here. Here on the bottom. There's an additional difficulty settings here. So if you do 2 and 1, if you do 3, you can do 2 and 1. Okay. But if you upload videos for 2 and 1, I'm going to give the house additional extra points if you just do them. Okay. The reference for the highest bonus is going to be the 3. No, the practice. I actually didn't remember that it was a practice. I thought that was level 1, but no, the practice is very straightforward. It's very straightforward. Okay. And the idea is for you guys to kind of understand again about these interactions with the charts. Okay. Questions with this one? Is it clear? So again, everybody has to turn it in. So it's not optional, but I'm going to be giving bonuses. Okay. And we'll see the videos on. We'll see the videos on Friday. Okay. Okay. Yeah, there's gonna be some interesting bonuses in the course. Because again, the challenging thing about this course is that it's really, again, if we were talking about dynamics or statics, we can physically do things, but with this, it's a bit difficult. It's a shame that again, the pandemic hit and you guys are in the middle of the pandemic with your classes and all that. But there were some traditions here at CETIS that were related to classes. So before the pandemic, we usually had what was called an engineering week. But it started out when I studied, it was a week, but it's actually just a couple of days where students presented experiments and projects. And people came over and all that. And usually for students like yourselves that were in second semester, I mean, you guys weren't doing these very complicated final projects. You're taking second or fourth semester. You guys are taking these courses. So in second semester, I think you guys took statics, right?
Yes.
So what are you going to do as a final project in statics? It's not that complicated. So we used to do a competition that was actually relatively, it's a tradition here in CETIS, which was the spaghetti structures competition. Have any of you, did you get to see that one, Ricardo?
Yeah, it was fun.
Yeah, so basically the challenge, and this had to do with statics, is that you had to do a structure. Like the structures you saw in statics. Like the structures, like for example,
A bridge.
like a bridge or something like this. This is a structure. You had to do a structure, but the structure could only be constructed with spaghetti and white glue. Those were the restrictions. And the contest was that everybody would go to the lab with their structures, and we would see how much force it would take to break the structure. And obviously, if you did the structure with the least amount of spaghetti, and I think the weight was also something that was considered, you would win the contest. And obviously, all of the professors in statics gave extra points for you guys doing the structure. Okay, so that was an easy way to kind of visualize that. But yeah, that was pre-pandemic. We also did the cardboard racing. Did you get to see that one, Ricardo? Any cardboard racing or any of you from? So basically, what that was is that you guys had to construct a cardboard car that could only be propelled by yourself somehow, and there was a race with cardboard cars, and whoever won the race won a prize and all that. And there was some really, the car could only be constructed from cardboard and white glue. And there had to be a driver, and the only way the driver couldn't, it's not like the Flintstones where you would could run with the car, that would be cheating. You would have to do some sort of mechanism to move yourself. It was really funny to see because some cars didn't make it, they just got destroyed. And other cars, people tried to do things that were very complicated. So you had like people rowing and stuff. And the design is actually the design that usually wins. It's a very simple design. But yeah, those were really fun events. Let's see if we can have those again. You got hopefully for us to have those before you graduate. Okay, so let's get back to this one, and we're gonna do. Okay, let's do this. I'm gonna do the first one, set up the first one, and then we'll do the Valentine's, and then we'll break. So the first situation is assuming that we have the two charges, and we're looking at this situation here. We're positioned here. What is the electrical field? The resulting electrical field at that point, okay? And so, let's see what's happening. If I place myself here at this point, I'm gonna do a mini free body diagram there. Again, I'm placed at that point. And I've got two charges. I'm gonna call this charge A and this charge B, okay? So if I'm located there at that point, and I wanted to draw the electrical field with regards to charge A, in what direction would I draw that electrical field?
Like this, going in and.
Well, something important here, Andrea. So we address these problems and don't get confused with something. Right now, we're just looking at charge A. Right now, at this point, we're gonna eventually get to the whole interactions, but we're going step by step so we can kind of piece everything together. So if I'm placed here, where would the electrical field with regards to A be pointing?
To the right, right.
To the right, correct. The electrical field with regards to A would be pointing to the right, and I'm going to call this EA. Why? Because we already saw that the electrical field of a positive charge is going to be going outward, so it's going to be pointing that way, and I'm going to call it EA. Okay?
Yeah.
EA, like EA Sports. Now, see, I don't know if the people at home, unless there's competition, the people at home seem to be asleep. So let me see if you guys are awake. Viviana, are you there? Viviana? Hi,
Yes.
hi, Viviana. So now let's look at charge B. If I'm located here in point 1, where would the electrical field with regards to charge B be pointing?
The opposite as EA.
Well, let's forget about EA. EA doesn't exist right now. If I'm here in this point, in point 1, I'm located here. And I'm looking at charge B, where would the electrical field of charge B be pointing? Let's remember that charge B, Viviana, is a positive charge. Okay?
Yes, to the left.
To the left. Okay, to the left. And I'm going to be calling this EB. Now, it's important, that's why I kind of corrected there. It's not the electrical fields of each of the charges are going to be independent of each other. They're going to interact, but they're going to be independent of each other. Right now, they're in opposing lines, but that's not necessarily going to be the same situation. Okay, thank you, Vivian. So is it clear that those two are the electrical fields? Now let's do some quick calculations here. EA is going to be the constant K multiplied by QA divided by the distance squared. This is going to be 9 times 10 to the 9 newtons meters divided by Coulomb squared multiplied by 1 times 10 to the minus 6 coulombs. What is the distance between, what is the distance that I'm going to consider for this situation?
2.
2, not 4. 4 is the distance between one charge and the other, but where am I located? I'm located here. Remember where I'm located. I'm located here in this point. And what's the distance between each of the charges? It's 2 meters. Okay. So correct. Well done. So it's going to be 2 meters squared. Enya, could you please help me out with that calculation?
Yes.
Thank you, Enya. And EB is going to be equal to K QB divided by R squared. This is equal to 9 times 10 to the 9 newtons meters times coulombs divided by Coulomb squared multiplied by 1 times 10 to the minus 6 coulombs. Whoops, divided by 2 meters. There's a squiggly line there. And let's see.
Professor, where did you get the 1 times 10 to the minus
Oh,
six?
good. So here it says that each of the charges is 1 microcoulomb. So remember that micro is to the -6. We're going to be seeing a lot of milli, micro, and nano, and maybe even pico. So milli is to the -3, micro is to the -6, nano is to the -9, pico is to the -12.
Where did you get the milli or that?
Excuse me?
Where did you?
Well, oh, here in the problem, it says 1 microcoulomb,
Okay, okay.
Uh,
That's to the -6.
-6. Micro is to the -6.
PC is micro. It says PC, right? Because I can.
No, it's this here, if we do a zoom, it's 1 micro column. It looks like a P, but it's a
Because I
mu.
can see.
It's small. It's actually the image is small. Anya, do we have the value?
Yes, but I don't know if it's correct.
Oh, let's see.
It's 2,250.
I got the same thing.
Perfect, 2,215 newtons. And actually, I'm not gonna ask anybody to calculate EB. Why is that? It's the same values, if you notice. It's the same values, so EB is gonna be the same. So what is going to be the resultant? I'm gonna call it the E resultant. The resultant electrical field is going to be, according to the free body diagram, the interactions of these. So right now, both of the electrical fields are on the x-axis. We don't have them in y. So it's going to be the positive minus the negative. EA is going to the left, the right. So it's going to be positive. EB is going to the left, which is going to be negative. Remember that we draw the free body diagram because of those references. And so this is actually going to be 2,250 newtons minus 2,250 newtons. So the resultant electrical field at that point is going to be 0. Oh, I made a mistake here. Just let me correct that. The units, it's newtons divided by coulomb. Forgot about that. Newtons divided by coulomb.
So that would mean that the particle or whatever you put in there is in equilibrium?
Exactly, Ricardo. That means that at that point, even though there are electrical fields interacting, at that point, the electrical fields are nulling each other.
Absolutely.
Exactly. So if the way you expressed it is completely correct. If I were to put a charged particle at that point, nothing would happen. Or going back to the electrical field hockey, if I were to put the puck there, the puck would not move because the fields are canceling each other out. That's not necessarily going to happen in all of the situations. It's happening in that situation. Okay, good. Questions with this one? We're going to be doing the 5 situations, which are different, but in this particular one, we're going to have 0 newtons divided by coulomb. Okay, questions with this one? Over at home, are we doing okay? Questions? Okay. Questions over at home? Let's have some reactions at least. Questions, everybody okay? Good. Okay. Okay, we're gonna do the rest of them in the next session. Okay. And this is gonna be updated. Okay, so I saw that some of you uploaded your the poems. I read them and they were very entertaining. So remember that it's not mandatory to do so. But does anybody want to share their poem with us so they can get some additional points for them in their houses. So let me, I don't want to show the poems here to be respectful of that. I just want to see who. Oh, so but a bunch of you did. So I'm just gonna, oh, it's good that you put them in PDF because in the other group, they put them as posts, so I can show, they actually showed them there. They want. So I'm just gonna go in order and ask you, do you want to share yours, Andrea? Go ahead, please.
Like start?
Yes, go ahead.
My life was normal until I met you. You accelerate my heart and turn on my feelings as you were a thunder. You're the electricity of my heart that keeps it beating, and I'm glad that it beats only for you. When I saw you, I felt shocked, like if you were an external force acting on me. I want to confess you that you are my other half. You are my proton and I'm your electron. Us two being attracted is a law. We were made for each other. Never doubt about our love. My heart will always be your electromagnetic field. I will always support you on your negative days as well as on your positive ones.
Nice. Well, good job. Well done. And that was nice. It's very well thought out.
So if we read the poem, we have additional points.
It's additional, so if you turn it in, it's already points. If you'll read it, you'll get more points. But you don't have to, again, it's not. So, Lisa, do you want to? Okay, go ahead, Lisa. Well, you can do one of those like in the movies, like the disclaimers. It's all of the contents and accounts represented in this poem do not represent real or fictional.
I didn't like know what to put, so I took out of some versions of Taylor Swift.
It's a Taylor Swift electricity and magnetism theme. Of course, we want to hear that, but it's a bit intriguing, so go ahead.
Remembering him comes in flashbacks and echoes. His love was a magnetic field that kept my love sealed, and I never knew I could feel that much. We were completely opposites, that's why we attract. Our love was magnetic, something about it felt like home somehow. It was like a love story that crashed like a storm. Knowing you was like energy fueling my soul. Back then, we didn't know we were built to fall apart. We were dancing to our favorite song till the gravity was too much. Even after all, our radiation converted to art, because together or apart, you will always have my heart.
Nice, well done. I'm curious as to what parts of those are Taylor Swift tunes. I was in my head, I was trying to match them to the melodies. Good, nice job, nice job. These were actually better than I expected. Enya, do you want to share yours?
Yeah.
Go ahead. Please turn on your camera because we need to see the emoji like we're seeing here in class. Go ahead, Enya.
Okay. Today is Valentine's Day, the one day full of cliches, when people are grateful for the relations and the power on the expectations. Love is like energy. It can neither be created nor destroyed, and it is also full of charge. It is not easy to find your other half, but as you may know, opposites attract. You will know that they're the one just by applying the famous Coulomb's law, calculating the force that will keep you together and decrease the one that is pulling you apart. Create your own electric field together and disperse the energy that you have created. And like charges Q1 and Q2, either QT.
That was very nice. I remember reading that one and I stood out the cliches. You used Coulomb's law and you actually used notation, which was very good. Well done. Well done. Let's see. We've got some volunteers here. Let's see, Giselle, do you want to share yours?
Yes.
Go ahead. Please turn on your camera. Go ahead.
So it says, the power of love is a mystery, how we are always attracting each other. Even though we are complete opposites, no force can make us bother. It shocks me every time I see you. Your energy fills me with love. What I feel for you is magnetic and electricity straight to my heart. the generator of my smiles and repeller of my sadness. This Valentine's, I want to tell you, thank you for all the happiness.
Nice, well done. I like the generator of happiness and the repulsion of sadness. Nice, well done. Yes, let me see. Estrella, would you like to share yours?
Yes.
Go ahead, please.
Okay. There is a magnetic field that is giving my love seal. A force so strong it is intense, just like an electric fence. That shocks me each time we touch, but I just can't get enough of this static overflow. I'm just about to blow and release a shock so large, the amount of my discharge will send waves of love right through the core, soul, and heart of you. Beams of romance, I will shoot at you, looking very cute. All this energy is warm like an electrical storm, flashing bolts of big bright light, making a romantic night.
Nice, well done. Well done. These are very good, very good. Well done. Nice. Alejandra, would you like to share yours?
Yes,
Go ahead.
I had tried once and tried once more to find the one that would make me whole. But I merely am a negative force, negatively judged, what could be worse? All around me are others like me, alone and negative, wandering free. But when I saw you, the young in my dreams, your energy so positive, nothing like me. You were not repelled like others before, some inexplicable attraction pulled me closer even more. Now you're by my side, we can be pull apart, and those who did try, you're a force stronger than my love.
Nice. I like that one. That was good. That was good. And not that the opposites attract thing and also the play on the charges. That's good. I like that. And it had a happy ending. I like that. Well done. Well done, Alejandra. Viviana, would you like to share yours?
Yes.
Please.
You have always been so positive. I have always been so negative, but that is why our force has always felt stronger for each other. Our love is like an electric field. All our love are the charges. The greater our love is, the stronger our field is. The closer we are, the stronger we are. And isn't it just so pretty to think all along there was some invisible magnetic field attracting you to me? There will always be positive and negative charges that would try and repel us from each other, but our love and force together is greater than any net force against us.
Nice. Well done. You used the term net force. That was good. That was good. And last but not least, Ricardo, would you like to share yours? Go ahead.
Okay. I am drawn to you like a magnet. Our poles opposite get in tune. Your world is my planet, and the obstacle of destruction I'm immune. You are my felicity, your smile, my electricity. We from insulators, we conduct our own fate. Our hearts are like oscillators, you're my true soulmate.
Nice, and I like the word you use the word insulators, which is not easy in a poem. That's why I like the movie Encanto. If you see it in Spanish, they use the word crisalidas in a song that makes you feel. And Huracán de Jacarandas, which is really not easy. So using the word insulators in a method, that was well done. Well done, you. This exceeded my expectations. I'm actually in a good mood because of your poems. I hope you have a good Valentine's Day, and I'll see you guys on Wednesday. Over at home, bye as well. You did a good job at the
Thank
poems
you,
as well.
Professor. Bye.
Happy
Thank you, Professor.
Valentine's
Bye.
Thank you
Day.
for
Thank you, Professor.
it helped with the sugar that I needed.